Now we are going to see some classic RNN architectures. So the first basic RNN architecture is this one. You have the inputs at the bottom. Just above, you have one hidden layer, and above that, the output layer. Note that the inputs are ordered since the structure of the input is a sequence, here denoted with the time varying from 1 to 7. The notion of time is just used here to remember that there is an intrinsic order in the inputs. Each input is fed to a hidden state, or equivalently a neuron in the hidden layer. The hidden state takes also the output of the previous hidden state as input. This allows the network to pass information through time, or equivalently through the hidden layer. Each hidden state produces a vector which is fed to the output layer. The RNN architecture is dramatically different from a classical neural network in which you would have connections between all inputs and all neurons in the hidden layer without any connections between neurons of the same hidden layer. This will be useful to model sequences. We now introduce some notations to describe precisely how each neuron of the hidden layer operates. There is an initialization of the hidden state with H0. Then the first hidden state takes as input H0 and X1 and produces H1, which is fed to the next hidden state and to the output layer. The output layer produces predictions denoted by Y hat. A major difference between classical neurons and neurons in RNN is that neurons in RNN, or equivalently hidden states, produce vectors instead of scalar. So here all quantities H0, H1 and so on are vectors and not scalar. The size of the hidden state, its dimension, is an important parameter of RNN. More precisely, the operation used to create the next hidden state Ht is given by the hyperbolic tangent applied to a linear combination of the input xt and the previous hidden state Ht-1 plus a bias Bh. This is written in the first formula. Here, the hyperbolic tangent is applied component-wise, meaning that it is applied to each component of the resulting vector separately. This formula closely resembles that of neurons in ANN, except that here, since we have vectors as inputs, the weight WHH and WIH are matrices. Finally, the output is given by the softmax function applied to a linear combination of the components of Ht plus a bias B out. Here are some more complex RNN architectures. RNN A is nothing but the same network as before, in which the hidden state is computed via an MLP, multilayer perceptrons, the same as ANN, applied to the linear combinations of the inputs and the previous hidden state. Hence, the hyperbolic tangent is replaced by a MLP. This can create more complex RNN, which may be useful to model complex data. RNN C has almost the same architecture as RNN A, but the output layer is replaced by a MLP. RNN B contains shortcut connections between hidden states. The components of one hidden state are used by, for example, adding the components to the new hidden state. This is the same idea as in ResNet. These shortcut connections may help the optimization procedure. RNN D contains a stack of hidden layers which communicates between each other. In the first picture I showed you with blue, red and green rectangles, it would be equivalent to have two lines of green rectangles which corresponds to two hidden layers. Bidirectional RNN are also frequently used to handle text data. You see in this plot that you have two hidden layers, a first one below that goes from the left to the right, and the other top that goes from the right to the left. In this way, a prediction can result from both the information before and after the corresponding position in the input sequence. The prediction is given by the formula below. Bidirectional RNN can be useful, for example, if you want to translate sentences because the meaning of one word can depend on the words before but also on the words after. Because connections are directed in both ways, this network is able to leverage on the dependencies of one word on the previous ones and on the next ones. Here are some other types of RNN. The last reference is a very good review on RNN. Even if this paper was published in 2017, it gives a very good overview of the different strategies that can be implemented with RNNs.